Hi everyone, welcome to the lab. In one of my previous videos I repaired Roland V-Accordion model FR7X, and in the process I noticed that it had lithium-ion pack in it instead of the original nickel metal hydride pack. I did not investigate at that time, but later on I found some information online. Apparently lithium-ion packs exist, someone came up with the design. I don't quite like it, at least on the first glance, so I decided to investigate and finally got around to this. So I borrowed this pile of stuff. First of all, this accordion, this time FR8X model, which has a charger built in. The only external thing is this 24 volt power supply. And I also have this charger and pedal board for model 7, which I repaired in my previous video, and I was told that model 7X has exactly the same charger and pedal board. And also I have these three battery packs. This original Roland battery pack, which is branded Sanyo. This replacement pack, which is also nickel metal hydride. It is branded FDK, which is a well-known company in Japan producing batteries, and this lithium-ion pack from unknown manufacturer. So let's take a look. Let's take a look at the original pack. We can see 1, 2, 3, 4, 5 rows of 1, 2, 3 and 4 cells. This thing is just to help pulling it out from the battery compartment. So 20 cells in total. Nominal voltage is 1.2 volts per cell, or 24 volts for this pack. Minimum discharge voltage is between 1 and 1.1 volts per cell. I'm not sure what the threshold is in these accordions. We will measure that later. And the maximum charging voltage is not well defined for this chemistry. Charging is usually done with constant current until some end of charge event. We will talk about that later. And usually that maximum voltage is between 1.5 and 1.6 volts, just to have some idea. It can vary with different cells from different manufacturers and temperature and so on. So let's say between 30 and 32 volts for this pack. The interface is this Molex connector with the 3 pins used out of 4, which are positive, negative, and this blue one is temperature sensor, which is a 10K thermistor between negative and this blue wire. Here it is, currently sitting at 9.37 kiloohms. Because it is 10K at particular temperature, let's say 25 degrees C, and it goes down when temperature goes up, so it's called NTC, or negative temperature coefficient thermistor. Now let's take a look at the lithium-ion pack. I found this page on the accordiongallery.com website presenting new and improved battery for the Roland 7, 7X and 8X accordions. DR600 battery pack designed by Duby Rainis. I probably mispronounced the name, sorry about that. There is a link to a YouTube video, we can take a look later. And some parameters here. Lightweight, 600 grams, which is about half of the weight of the original Roland battery, which is excellent. I'm sure people love that part. A long lifetime, more than 1000 charging cycles. Well, maybe if you use the cells within specifications, which is not the case here. 10 to 12 hours of playing time. AWT lithium-ion cells with temperature and short protection. I am not sure about the short protection, I don't think so. And here is the pack we have. And the first thing I don't like is that I don't see any battery management system, or BMS. I believe every lithium-ion pack should have a BMS, which provides protection from overcharging, over-discharging, overcurrent, short circuit, and in some cases it can balance the cells, which is a very good feature to have for the long-term life of the pack. Now let's take a look at the YouTube video. It is 6 minutes, some text here, then some pictures, and I believe about half of the video is demonstration of the runtime of the pack using 8X model accordion. It was set to play in demo mode until battery pack died, and that took allegedly about 18 hours, which is excellent, of course. But what I did not like here, the second thing I did not like, is this claim that charging voltage cutoff of 31.5 volts is proper for 7 cells of lithium-ion. Is it really? First of all, I'm not sure about this voltage. We will measure later. Assuming it is correct, we divide it by 7 and get 4.5 volts per cell, which is way too high. I don't think we can say it is proper. Let's see, here is a picture of a cell used in the DR600 pack, AWT, 26650 cells, 4500 milliamp hours. Here is the schematic, 7 cells, temperature sensor, which is called a thermistor, not thyristor, and the thermal fuse, which is 120 degrees C in this case. And I believe that claim about having short circuit protection is about this fuse. But thermal fuses are not really designed to provide overcurrent protection. They are designed to melt at particular temperature. So I think that claim about having short circuit protection is bogus. I also found this page, Accordion Shangri-La, with the same name on it. It is somewhere in Israel, so it must be the right one. And here we have some more technical details. The same cutoff voltage is mentioned, 31.5 volts. Charging current is mentioned as well, 1800 milliamps. And a very strange claim here that the typical maximum charge voltage is 4.4 volts. Checking the specs of few manufacturers, it seems that most will allow 4.6 volts per cell. I have never seen 4.4 volts specified, let alone 4.6 volts per cell. The typical I've seen is 4.2 volts with rare exceptions. And I checked many specifications from leading manufacturers like Panasonic, LG, Sanyo, Samsung, and so on. Look at this, for example. DR250 pack is based on Panasonic 18650 cells. Charge voltage 4.2 volts, of course. DR600 pack is based on AWT cells. Maximum charge voltage 4.2 volts plus minus 50 millivolts. Another example is here, Panasonic cylindrical series, 4.2 volts everywhere except this special model with slightly modified chemistry. Here we have 4.35, and if we add that typical tolerance of 50 millivolts, we can potentially say that maximum here is 4.4, but this is not typical, and I have never seen anything like 4.6 at all. And here I found on LinkedIn this AWT battery technology. with website pointing to the Alibaba store, and here it is. Same cells here, and just to double check the specifications, charge upper limit voltage is 4.2 volts plus minus 50 millivolts. So this is typical. I started measuring things to understand what's going on. Here I am charging the original Roland pack in the accordion and measuring the voltage of the pack. And it is approaching the end of charge. Charging finished, and as we can see, the maximum voltage was 29.95 for this pack. I'm not sure what charging algorithm is used here, but as I said, I don't think there is a particular voltage threshold for charging nickel metal hydride batteries. And this is the discharge with the accordion playing in demo mode, but in this case with the volume set to 0, so not much energy was spent on the amplifier. And it took about 9 hours to discharge, and the minimum voltage was 22.37. And now the same test for the lithium-ion pack. This time the maximum voltage was 30.95 and the minimum voltage was about the same, and it took about 12 hours to discharge. Then I decided that it would be nice to also measure the charging current, so here I am using this current clamp connected to this meter, and it turns out that in the accordion the charging current is about 1.2 amps. But I also wanted to measure the voltage on the temperature sensor, and I realized that this approach is not convenient anyway. I wanted to have all these measurements in one place, so it would be easy to time correlate them, perhaps plot together or something like that. So I decided to use a different approach. So I ordered some Molex connector housings and pins for them to build a few connectors. And I built this test adapter. The battery pack plugs in here, this end goes into the charger, and there are 3 pairs of wires for measurement. The orange pair is to measure the voltage of the battery pack, the blue pair is to measure the voltage on the temperature sensor, and the green pair is to measure the voltage drop across this current shunt, which is 0.1 ohm, 1%, 5 watt resistor. So for 1 amp of current we should see 100 millivolts voltage drop across this shunt. Not a big drop, should not distort things too much, and easy to measure. And here it is in use, connected to this Agilent switch control system, which has a relay multiplexer module in it. And that module can switch up to 10 input pairs to 1 output pair, and that pair goes to the rear input of this multimeter, and both instruments are connected to my computer through GPIB interface, and with a small script in Python it's quite easy to measure things and write the results into a log file. Let's briefly look at the charging process. Wikipedia is a good source for such things. Here is an article about nickel metal hydride battery with different charging methods described. Trickle charging, delta V, sometimes called negative delta V, and delta T, where T is temperature. Here they are. Trickle charging is a slow charging with current of about 0.1 C, and this terminology is tied to the capacity of the pack. So 1 C current would be whatever current is necessary to charge a pack in 1 hour. So in our case the nominal capacity of the original pack is 4500 milliamp hours. And that means 1 C current would be 4.5 amps, and 0.1 C would be 1/10 of that. So this process should charge a pack in 10 hours theoretically, but because there are some losses, in practice it's a bit longer, let's say from 12 to 15 hours. And clearly this is not what is happening in this charger. For faster charging, one of these two methods should be used, or maybe both. Negative delta V method is trying to detect a voltage drop, a small drop at the end of charge, and the delta T is trying to detect a temperature rise at the end of charge. And both these signals can be quite faint, especially if current is not very high. So usually, in addition to these primary methods to detect end of charge, some sort of secondary method is used, or a combination of some secondary methods, like a voltage threshold. If a voltage reaches some particular maximum, then charging is terminated, or a temperature threshold. If temperature reaches particular maximum, then charging is terminated, or some timeout. And here is another good description I found. They are talking about different chemistries here, and in particular there is a useful plot about charging nickel cadmium and nickel metal hydride batteries. And as we can see here, the voltage drop at the end of charge is less pronounced for nickel metal hydride batteries, so it might be harder to detect. And this is the temperature rise, which also can be not very pronounced, especially if the current is not very high. And here they are talking about charging current between 0.5 and 1 C. But in our case, the charging current is about 1.2 amps, which is even below 0.5 C. And here they describe constant current, constant voltage method for lithium-ion batteries. And as I said many times before in my previous videos, charging lithium-ion chemistry is easy. All it takes is a current-limited power supply with a particular target voltage set, usually 4.2 volts per cell, or in our case of 7-cell pack, it should be 29.4 volts. And in the first phase, when voltage is rising and the pack is charged with constant current, which is based on either what particular type of cells can take, or with modern cells which can take a lot of current, it might be based on something else like cost considerations for the charger. Some reasonably priced charger which can charge in a reasonable time, let's say a couple of hours or so. And when voltage reaches the maximum, then current starts dropping, and there is no need to cut off at particular point. The current will drop to almost nothing and stay there, but just for convenience, to show the user that charging is done, a particular current threshold can be used. Let's say if the current drops below 50 milliamps or something like that. Now let's look at what actually happens. This is a plot of charging one of the nickel metal hydride packs in the accordion, and unfortunately I forgot to make a note which one. I think it was that FDK branded pack. It took about 2.5 hours to charge, and I did not plot the current. It is not interesting, just a straight line. In the accordion the current is about 1.23 amps, and from the external charger it is about 1.3 amps, which is about the same. So this blue line is the voltage, and the red line is voltage change on the thermistor, which I inverted because it goes the other way around. It goes down with the temperature going up, so I just subtracted it from the maximum voltage, which was here and corresponds to minimum temperature. And from some experiments I determined that the voltage change is about 0.035 volts or 35 millivolts per degree C. So this whole rise of the temperature is about 6.5 degrees C. And this whole thing is a bit surprising to me. I did not expect to see something like this. First of all, it seems to me that the negative delta V is around here, but it is quite faint and was probably missed or not even used in the algorithm. So charging went into slight overcharge, I believe. And the second, I don't see a steep temperature rise around this region. It is almost flat here. So it is not clear to me what algorithm is used in this charger. Perhaps it hit a maximum voltage threshold, but in that case I would expect that voltage to be the same every time, which does not seem to be the case. We have seen almost 31 volt before, but this time it was just slightly above 30.2. However, in this case I introduced that current shunt, and this is the voltage on the battery side, so on the charger side it should be higher by about 120 millivolts. So I would think that the actual voltage on the charger side should be around here, 30.4 or something like that. And at this point, when charging is done, I can hear some relay clicking and the light on the charger changes from red to yellow. And I excluded all measurements after that from this plot because it looks confusing. The voltage on the temperature sensor disappears, and that big jump messes up the scale here. This is my experiment to have some idea how this voltage on a thermistor corresponds to a temperature. I'm using this black thermistor from an old lithium-ion laptop pack, and I found that if I hold this charge button, then the voltage is supplied and I can measure it. And I hope this thermistor is similar enough to those built into the packs under test, but you never know, so there is some degree of uncertainty here. And also they are not quite linear, but I think it can be assumed that they are almost linear in a narrow region of interest, let's say from 25 to 30 degrees C or something like that. And I put this temperature probe right next to the thermistor, and it is connected to this Fluke multimeter. And I waited for some time for the temperature to stabilize before making this measurement. And now I'm trying to bring the temperature up, waiting for it to stabilize and holding that button at the same time. And this plot is about charging the other nickel metal hydride pack using the external charger. I believe this time it was that Sanyo branded pack, but I'm not entirely sure. This time it took about 2 hours to charge, and this looks quite different. First of all, this negative delta V seems to be more pronounced. But again, it was either missed or maybe not used in the algorithm, and the process went into some overcharging. And the temperature profile looks quite different. There is no flat region here anymore. But again, I don't see a steep rise around this point. If anything, it slowed down a bit. But the overall rise seems to be about twice the previous one. But it can be because of different thermistor, you never know. So the outcome seems to be about the same, meaning that the process went into some overcharging and terminated using unknown criteria slightly above 30 volts. And this is lithium-ion pack charged by the accordion, and this looks quite different. The voltage does not show that flat region with negative delta V at all, because this chemistry just does not have that effect. And the temperature profile is mostly just magnified noise, because this whole range is about a few degrees C. So this time charging took 3 hours and let's say about 20 minutes and terminated around 30.8 volts. And this is lithium-ion pack charged by the external charger. The voltage profile looks similar, but this time terminated around 30.1. The whole process took, let's say, about 2 hours and 45 minutes. Perhaps the pack was not completely discharged to start with. This was not the main point. And the temperature profile looks a bit different, and the change was more substantial, perhaps around 10 degrees C or something like that. But unfortunately, I'm not doing this in an air-conditioned environment. So part of this change might be due to ambient temperature change. Perhaps I should have measured ambient temperature separately at the same time and subtracted to compensate. There is no limit to perfection. Going back to this page, I'm not sure where this voltage of 31.5 came from, and this current of 1800 milliamps. I have not seen anything like this. The current is about 1300 milliamps, and the maximum voltage I have seen was almost 31. So the overvoltage problem is not as bad as I thought, but I don't think this changes things much. There is still some overvoltage, and my primary concern is the absence of BMS. And BMS would almost solve the problem with overvoltage. Ideally, we should not rely on BMS to terminate the charge by triggering overvoltage protection, but that would be a huge improvement compared to what we have now. Let's take a look at some BMS modules. I found this one on eBay, which looks quite tempting. 7S, 29.4 volts, with balancing, which is excellent, and just $4.54 with free shipping from China. If this works, it should be quite a good option, I suppose. Look at this diagram. The key feature in BMS is that all cells are measured individually, and that is for safety and for balancing as well, if that feature is supported. Sooner or later, pack will start degrading, or some damage can occur, and let's say one of the cells goes short. Without BMS, that can lead to other cells being overcharged, and that can lead to a disaster. You don't want to burn your house down if your battery pack fails. But with BMS, if any of the cells goes out of range, below some minimum voltage or above some maximum, the whole pack will be disconnected. This must be for balancing, I suppose. 7 big resistors. If close to end of charge some cells charge faster than the others, this circuitry will dump the excess current into the corresponding resistors and try to compensate, up to a point of course. And if cells are healthy, the pack will eventually balance and stay that way, and that should improve the lifetime of the pack. Some specifications here. English is not very good, but not a problem, we get some idea. Here's the size, it looks okay, it should fit just fine. Maximum continuous current is 15 amps, which is overkill for our purpose, but I have never seen 7S modules with lower current. A downside of this is that the overcurrent protection threshold is set too high, perhaps above 20 amps or something like that, but this is not essential. Overcharging voltage threshold is 4.25 plus minus 50 millivolts. This must be over discharge voltage threshold 2.5, which is a bit too low, but not a problem. And short circuit protection, of course. Looks great. I will try one of these. Here is another module on eBay. They sell 6S and 7S modules with different maximum currents, so I selected here 7S with the lowest current, and they are 860 with free shipping from Hong Kong. And I think this one does not have balancing feature. But anyway, I wanted to have at least one more option, just in case that one does not work as advertised. It's time to build an experimental pack with BMS. This is an old laptop pack. I opened it some time ago and it was sitting around waiting for a good opportunity to start a new life. These are Samsung cells, 26D, so the nominal capacity is 2600 mAh per cell, and this is a free serial, free parallel configuration. Here is the other side. Nominal voltage is 11.1 volts, which is exactly 3.7 volts nominal voltage of one cell times 3. Capacity is 85 watt hours, and here we can see minimum 7.26 amp hours, and divided by 3, this gives us 2.42 amp hours per cell. Before spending time on it, I decided to test it. This is measuring the capacity of the first section of 3. I decided to test section by section, just in case they degraded differently. And I have a separate video how to use Agilent power supplies of this series to charge and discharge lithium-ion batteries. I will put a link in the description. And here is the result. All 3 sections are very close. Let's call this 7100. Divided by 3, we get about 2367 per cell. And divide that by 2600 nominal, we get about 0.91. So about 91% of nominal. Not bad at all. Partially taken apart, this is a temperature sensor. We are going to reuse it. 7 cells are ready for a new pack. All wires for BMS are soldered. The module is attached with a double-sided sticky tape, just like these pieces here between the cells. Reusing the temperature sensor. The experimental pack is ready, and it is a small pack compared to the original pack, so it must be much lighter. And I believe these original cells are the same in size as these typical 18650 lithium-ion cells. And by the way, this means 18 millimeters in diameter and 65 millimeters long, and I'm not sure what that 0 at the end means. Probably nothing. So we should be able to fit 14 cells in a pack. This pack has 12 cells on the bottom 3 rows. So we add 13 and 14 on top. And this leaves more than enough room here for BMS. And modern cells can have more than 3000 mAh capacity. So it should be possible to build a pack with more than 6000 mAh of capacity. And this pack has 26 mm cells, and it is 4500 mAh capacity. So we can go higher than this if desired, but it's not going to be much lighter than the original pack, I suppose. By the way, this module has arrived as well, but they sent me a wrong one by mistake. This is for 6 cell packs, not for 7. They promised to send me a right one, but it will take another few weeks to arrive. And here is the plot, charging of the experimental pack with BMS using the external charger. And look at this steep temperature rise at the end of charge. I believe this is the balancing process. Some of those balancing resistors start heating up. I fitted the temperature sensor right under the BMS. And this seems to be a few degrees C in a few minutes. And the cutoff voltage this time was around 29.5, which seems to be the overcharging protection threshold in the BMS. And this is another plot, this time using the charger in the accordion, and it looks almost identical, but the temperature rise is a bit lower this time, probably because the cells are balanced better now. So everything works just fine, and luckily both the accordion and the external charger don't mind this sudden cutoff by BMS. I was afraid that it might look confusing, show some error or something like that. However, this is just the first phase of charging for lithium-ion chemistry. Ideally, at this point, the second phase should start, which is the constant voltage phase. But these chargers are not designed to do that, so we'll lose some capacity, and that might be quite substantial, from 10 to 20% or something like that. I'm not sure exactly, we can try to measure that. So I fully charged and discharged this pack using this lab supply, and I measured 2419 milliamp hours. And then I charged it using the accordion's charger, which does only the constant current phase, and I discharged it again using this lab supply, and I measured 2119 milliamp hours. And that is about 12.4% drop. And that may vary with different cells from different manufacturers. One possible solution to this is to use a proper lithium-ion charger, but that would take an extra charger, an adapter to connect this pack to it, and would require taking the pack out of the accordion every time to charge, which is not very convenient. So I'm not sure this is worth the trouble. You may want to just tolerate this loss of capacity, especially with a high capacity pack. I wanted to try one of these cheap chargers sold on eBay from China, 29.4 volts, 1 amp, just under $8 with free shipping. So I ordered one, but unfortunately I received a non-working unit, so I cannot really recommend them. But it is hard to make decisions based on one sample. I wanted to try one more thing. What if we could arrange something between the charger and the battery so that it would be almost transparent during discharging and during charging as well, but until the voltage reaches the target of 29.4, and at that point it should limit the voltage on the battery side. I think it should not be difficult to design such a thing. Here it is, based on classic LM317 voltage regulator. Capacitors here are not really necessary, just in case for stability. This adjustable voltage divider is to set the target voltage. So during charging the input voltage will go up, and this regulator should pass it through, with some drop of course. And when the input voltage reaches the target, it should start regulating and limit it on the battery side. And during discharging, the current should flow through this Schottky diode. And here it is. I built this thing and trimmed to have the right target voltage. As you can see, 32 volts in, 29.4 out. And I built this test adapter. We can put it between the battery and the charger, and I attached one more pair of wires here to measure the voltage on the battery side. Here it is in use. It works, but the voltage drop during charging is too high, about 2.5 volts, and because of that the regulator is running too hot. I measured about 83 degrees C. Clearly this is not acceptable. I found this low dropout equivalent to replace LM317. This thing should have voltage drop about 1 volt, so this might work. I found these LT1085CT regulators on DigiKey. They are expensive parts, $884 a piece. Let's try. A couple of them arrived from DigiKey. Let's give this a go. This time the voltage drop on the regulator was just under 1 volt, and the maximum temperature was about 55 degrees C. Not too bad. This might work, but I doubt this makes much sense for a pack with BMS. Extra cost, extra complexity, extra heat, and a minimal benefit. Just a little bit lower maximum voltage and a bit more capacity loss associated with that. Perhaps it would make more sense for a pack without BMS. I would not recommend having packs without BMS at all, but some people already have them, so this might be a partial fix. However, I have not tried running this in a closed battery compartment. Perhaps extra heat could trigger over-temperature protection and terminate charging prematurely. So, let's try to draw some conclusions. First of all, I believe that modifying chargers is out of question. These are expensive instruments and I don't think people would want to modify them, especially the new model with charger built in. And I don't even know how to modify them. They are not designed to charge lithium-ion chemistry. The second phase, which is the constant voltage phase, is missing. The best thing is to have a pack with BMS. That should solve the problem with safety, but still there is slight overcharging and lost capacity. Further improvement would be to charge it with a proper lithium-ion charger, but it is less convenient. You need to take the battery pack out every time to charge, and you need to have that charger, and you need some adapter to connect the battery pack to it. And most probably those chargers cannot read the temperature sensor, they just don't have that feature. At least the cheap ones don't. And that's why I believe that charging this battery pack without BMS with an external lithium-ion charger does not solve the problem. It solves one problem with overvoltage, but there is still another problem with failing cells. And without temperature control, I am not even sure that it is a better approach. We would rely entirely on that last resort thermal fuse, and I am not even sure if that thermal runaway goes that far. It would be easy to stop without a fire extinguisher. So I firmly believe that a pack without BMS is a bad idea. And why? This module is just $5 delivered. And it works great, I'm quite happy with it. So I'm afraid I don't have a very good advice for those who already have these packs. The best thing would be to fit some BMS to those packs, but I'm not sure how difficult that would be. It depends on pack construction. If it's easy to solder wires between these cells, then it might be a simple matter of removing this wrapping, soldering wires, adding BMS, and putting some other wrapping on. Otherwise, it would take rebuilding this pack completely, and that would be a lot of work and might damage the cells. Anyway, I hope this analysis was interesting and useful. Thanks for watching. Bye.